Greetings, students. Today we're going to be looking at graphs of polar functions. So we just in the previous lesson had talked about how we can convert polar functions into Cartesian functions and Cartesian functions back into polar functions, which makes you think that maybe these two things are equivalent, and it turns out that's not exactly the case, because there are polar functions that are not really feasible to create graphs of in a Cartesian setting. Mostly because they would fail a vertical line test, and it's rather difficult to do that. However, we can deal with these things in a polar graph setting. So let's start by talking about how we determine ranges for a polar function. And I'm going to do this just with an example. So let's say we have r equals 1 plus or 3 plus cosine theta. Now, the key here is remembering from first semester that the range for cosine is just -1 to +1. So in this case, the maximum value for r would be when cosine is 1, and the minimum value for r would be cosine is -1, since 3 is constant. So that would tell me that the range is the minimum value of those two numbers, comma, the maximum value. Let's do another example with another polar function, just to make sure we have it. So what if we have r is equal to 4 minus 3 times sine theta? Again, the key here is remembering what the range for sine theta is. And again, that's just -1 to +1. So if I replace sine theta with its minimum and maximum values, I get 7 and I get 1. So we'd say the range for this is then the minimum of those two numbers, comma, the maximum of those two numbers. Hopefully that felt pretty easy. It shouldn't have been too difficult. The key there is just remembering the ranges for sine and cosine, which was, again, something we dealt with first semester. Next topic that we're going to talk about are types of symmetries. So perhaps you remember from first semester that we have 3 types of symmetry. We have x-axis symmetry. Oops. We have y-axis symmetry. And then we have an angle that I'm going to refer to as alpha, point symmetry with respect to the origin. And WRT is just my abbreviation for with respect to. So if you remember, we can test these symmetries by replacing the independent and dependent variables with a different version of that independent or dependent variable and seeing if we are left with the same equation. And we'll do some examples of this in just a moment so you guys can get a feel for exactly what I mean. But the key here thing to remember is for each symmetry what you need to replace in your equation. So this is the kind of the key here. Okay, so those are the properties that I'm going to be using in each of these example problems. And the obvious next question would be, am I restricted just one type of symmetry per equation? And the answer is no, we are not. And we'll see that straight away in this first example. So let's say we want to prove that the function r is equal to 5 times sine 3 theta has y-axis symmetry, and, oh, I forgot to write that. And 120 point degree symmetry. Okay. So let's do the y-axis symmetry first. So what we're going to do is, remember, for y-axis symmetry we want to replace r and theta with negative r and negative theta and show that we get the same function back, namely that somehow this is going to simplify down to just be r equals 5 times sine 3 theta. So the key here is I'm going to start inside the parentheses. So 3 times negative theta is just negative 3 theta. And then if you recall back from first semester, one of our odd-even identities was this, that sine of negative x is equal to negative sine x. So I'm going to apply that here to move that negative sign from inside the sign to the coefficient on sine. And then if we divide both sides by negative 1, we're left with the original. So, because we replaced r and theta with negative r and negative theta, but this still simplified down to the original equation, I know that we have y-axis symmetry. Next, let's do our 120 degree point symmetry. So remember, for this one we have to replace r comma theta with r comma theta plus 120 degrees. So we'll start by taking theta and replacing with theta plus 3 or plus 120 degrees. If I distribute that 3, I get 3 theta plus 360 degrees. And now, if you remember back from first semester, that we have an angle sum formula for sine. It says that's going to be sine alpha times cosine beta plus sine beta times cosine alpha. I think that was back in chapter 6 that we talked about those, but I'm going to apply that property now. Didn't leave myself quite enough space there. So when I apply that sum rule for sine, I get this. Okay. So if you recall, back to our unit circle definition, cosine of 360 is just 1, and sine of 360 is 0. So that's going to leave me with this whole piece dropping off, because 0 times anything is 0, and 0 plus anything is itself. And 1 times sine theta is just, or 1 times 3 sine theta is just sine 3 theta. So I'm left with 5 times 3 sine, or 5 times sine 3 theta, jeepers creepers. And we're finished. So again, hopefully that wasn't too bad. Again, we had to use some previous definitions back from first semester. And if you had to look those things up when you're doing your homework, that's okay. But certainly those properties back from chapters 5 and 6 could become quite valuable in these sorts of problems. What I want to do next is talk about 2 typical types of graphs in polar function. And there's 2 that we're going to talk about here. The first kind is rose curves. Rose like a flower. So we'll just start with some general information. So the standard form equation is r equals a times cosine n theta, or r is equal to a times sine n theta, provided that n is a positive integer greater than 1. For rose curves, the domain is always going to be negative infinity to positive infinity. And the range is always going to be negative the absolute value of a, comma, absolute value of a. And as a direct consequence, the maximum r value is always going to be the absolute value of a, the number of petals in our graph is always going to be n, and we'll talk about what we mean by petals here in a second when we actually graph one of these on our calculator. And then we should talk about the symmetries. So if n is even, we have x-axis symmetry, y-axis symmetry, and alpha point symmetry. If n is odd and r is a times cosine of n theta, we have x-axis symmetry and alpha point symmetry. And if n is odd and r is a times sine n theta, we have y-axis symmetry and alpha point symmetry. Now remember, alpha is just an angle measure, so how do we determine what alpha is? For all three of these situations, alpha is just 360 divided by n. So think about it for a moment. Why do you suppose that when n is odd, it matters which type of function you have in terms of getting x-axis or y-axis symmetry? Well, if you remember back to first semester, cosine has x-axis symmetry also, but not y-axis symmetry. Is that right? I don't remember. That's the reason, though. It has to do with which one of these has which kind of symmetry. You'd have to think about it a little bit harder, and quite frankly, I'm doing this at 8 in the morning, and I don't recall right off the top of my head. But that's not material right now. I was just trying to come up with a way to remember it, but since I can't remember it that way, it's probably not going to be helpful to you to remember it that way. So let's do an example here where we apply what we learned and then look at the graph on our calculator. So let's say we want to analyze the graph r equals -6 times cosine of 5 theta. So the first thing I like to do is I like to write down my value for a, which in this case is -6, and my value for n, which in this case is 5. So once I know my value for n, I can also write down my value for alpha, because that's just going to be 360 divided by n. So in this case, my alpha is 72 degrees. So first things first, I notice that r equals -6 cosine theta is in the standard form for a rose curve. So the type of graph I have is a rose curve. I know the domain for all rose curves is -infinity to positive infinity. The range is always going to be negative, the absolute value of a, so in that case, -6, and then positive, the absolute value of a, which in this case would be +6. I know the maximum R value is going to be the absolute value of A, in this case the absolute value of -6. The number of petals, and we'll see what we mean by petals in just a second when we graph this on our calculator, is just n. and then our symmetry. So notice that n is odd. So if I go back above, if n is odd, and we're in the form a times cosine n theta, which is what we have, so we're going to write x-axis symmetry and 72-degree point symmetry. Okay. So to graph this now, we're going to open up our graphing calculator. Okay. So we've pulled up our graphing calculator. The first thing I'm going to do is go to my mode. I'm going to make sure I'm in radian mode, which I am, and in polar mode. So I'm going to go ahead and change that to polar. Then I'm going to go to my y equals menu. I'm going to type in my function exactly as it was written. So -6 times cosine 5 theta, and then close my parenthesis. I'm going to go ahead and set my window. So for the case here, all we need our theta, even though the domain is -infinity to +infinity, we know that the period for cosine is just 0 to 2 pi, so I'm fine with that. And then I just did a normal square window, so x is -10 to +10, and y is -10 to +10 also. You can't see the +10 because it's down below. Anyways, once that's all set, I'm going to go hit graph. And what you're going to see is something that looks kind of like a flower. And if we count each one of these guys are petals, I see 1, 2, 3, 4, 5 petals. So that's what our graph is going to look like. If you didn't get this to come out and you got just like some points, go back and check your mode because you're probably in degree mode. But you should be able to graph one of these guys on your calculator, and you should be able to describe some of these facts about it using the list of criteria we gave you earlier. Okay. The second type of polar graph that we're going to talk about is called Lemus curves. And probably need to spell this because the pronunciation and the spelling don't look really the same. So L-I-M-A-C with that little accent thing on it, kind of looks like a comma on the bottom of your C, O-N. And that's pronounced Lemus, not Limacon, as students are apt to say. It's a French name, I believe. Definitely European. So the standard form equation for a Lemus curve is R equals A plus or minus b cosine theta, or a plus or minus b sine theta, where a and b are both positive. The domain for all Lemus curves is -infinity to +infinity. The range is going to be a minus b, comma a plus b. The maximum R value is going to be, not surprisingly, a plus b. And there's 4 different types of Lemus curves, and we'll look at a couple of examples in a second. So we can classify them looking at comparing the a and b values in a certain way. So if a over b is less than 1, so remember that doesn't mean negative because the a and b are both positive. but it could mean like a decimal. We call this type of graph the inner loop, and we'll look at some pictures here in a second. If a over b is strictly equal to 1, we call this the cardioid. If a over b is bounded between 1 and 2, we say this is the dimpled. And if a over b is greater than or equal to 2, we call this the convex. And again, we'll look at some pictures of these four different types here in a second, just so that you get a good picture of this in your head. And the last thing we want to talk about here are the symmetries. And here the symmetries are very easy. If you have the cosine version, we have x-axis symmetry. And if you have the sine version, we have y-axis symmetry. Okay. So next up, let's look at some pictures to get something in our head for these 4 different types of Lemus curves. Okay, so what I have here is some screenshots of the calculator of the 4 different shapes or types for these Lemus curves. This first one is the inner loop, where you can see you have like kind of a circle inside of a circle. This one is the cardioid. So it's difficult at first to tell the difference between the cardioid and the dimpled. If we compare the two, they are quite similar. The key attribute to tell the difference between the cardioid and the dimpled is this shape here. Really needs to look like a cusp versus like, like a dimple. And I know that's subtle, and you'll do the best you can, but that's really what we're looking at there. And then this last one is the convex. If you remember back from geometry, the definition of convex, that'll make a lot of sense to you as to why we're calling that convex. So in geometry, we said that a polygon was convex if you can draw any segment drawn from like an internal vertice will never cross like an edge of the figure. So like this is not convex because I can draw from like here to here, and it will cross the edges of it. Okay, so let's do an example. And again, worth pointing out that, yeah, these may be difficult to tell the difference of just by looking, but you know what's really good at telling the difference between them and is super clear is these 4 criteria. So if you're not sure if it's like dimpled or cardioid or something, you can always fall back on these and it'll be super duper clear, because if you divide 2 numbers, that's pretty precise. So let's look at an example. So right away, because we have a addition or subtraction symbol in the problem, we know this is a Lemus. And here we can say that the A is 4 and the B is 3. Remember, the A and B are always positive, so you can ignore any subtraction symbols there. So we know that the domain is always all real numbers. The range is always going to be a minus b, which is 1, comma a plus b, which is going to be 7. So my max r value is going to be 7. And then if we look at for the type, remember we want to compare a over b. So that's going to be 4/3, which is bigger than 1 and less than 2, which tells you this is the dimpled. And since we're dealing with the sine version, we know the symmetry is the y-axis symmetry. Okay, so let's just kind of confirm that now with our calculator. So we'll pull up our calculator. I'm still, all my mode and everything is fine because I was just using this to do this other polar function just a moment ago. So I'm going to clear that one out of there and do 4 minus 3 sine theta. And my window and everything should be fine for this, so I'm going to go ahead and hit graph. And what I have is this kind of heart-shaped curve that is very much the dimpled shape that I was expecting. Is everybody okay with that? I sure hope so. Anyways, that's good. That's all we have for this section. You guys should finish up the last of the book homework. The assignment is on the PowerSchool calendar. I believe it is like 85 through 96. So that shouldn't be too bad, as most of this is just kind of using these criteria to answer some questions or graphing things on your calculator. Okay, we'll see you next time.